All right, everyone. So this is going to be our video all about momentum conservation. And we're going to start off similar to the demo I believe we did in class. If we haven't done it in class, then surprise! But we're going to be talking about two objects. Let's call them A and B. And they are colliding in some way, shape, or form. We might also call this an interaction. And basically, when two objects interact, they exert forces on each other. Forces on each other. Okay. Now, we've talked about how those two forces compare, right? We know that from Newton's third law, that when any two objects interact, the forces between them in that interaction, so the force from A on B and the force from B on A, are equal in magnitude but opposite in direction. That's what that negative means, opposite in direction. So they feel the same force, just in opposite directions. So B feels a force in this interaction, right? This is A on B, and A feels a force to the left, force from B on A. Okay. So with Newton's third law, we're going to kind of expand on that. So we know from Newton's second law that force is mass times acceleration. So let's pretend that there are no other external forces. So that means, on the object A, the net force is BA, and on object B, the net force is AB. So I could really replace this with the mass of A. This one's A, mass of A times the acceleration of A, mass of B times the acceleration of B, right? Now, these masses may or may not be different, right? But we know that the bigger the mass, the smaller the acceleration, right? Little mass means big acceleration. And that's why in car accidents, it's usually the smaller car that gets damaged. Okay? So let's take this one step further. Right? We know that any acceleration is a change in velocity over time. Right, so this is really negative MA, change in VA over T. Now, this collision happens in the same amount of time for both objects. It's not like one is colliding for longer. So these two T's here are actually the same, and therefore I can cancel. So then that gets me to MB, change in VB, is equal to negative MA, change in VA. Now, this idea of mass times velocity should, at this point, be looking a little bit familiar to us, okay? Because we know that momentum is defined as mass times velocity. Okay? So this m times change in velocity must really be the change in momentum of object B is equal and opposite to the change in momentum of object A. And this is actually how Newton's second law was actually written. It was written in the form of momentum. So what this tells us is in any interaction where the speed is changing, the change in momentum of object B should be equal and opposite to the change in momentum A with no external forces that could change momentum, like friction, etc. Okay. Now, these are the individual momentums, but what if we want to think about the system as a whole? Okay, well, if I think about the system as a whole, the momentum of the system, the AB system, is really going to equal the momentum change of object A plus the momentum change of object B, right? We talked about that before, that the total momentum of the system is just the individual momentums added together. We talked about that in a previous video. So it stands to reason that the change in momentum of the system should be the change in momentum of A plus the change in momentum of B. Well, we just said that the change in momentum of B is the same thing as negative change in momentum of A, right? As long as there's no external forces. So instead of change in momentum for B, I could say, all right, negative change in momentum for A, right? So really what that gets me to is 0. And this equation here is really what conservation of momentum means. This means that the total momentum of A, and it's usually referred to as a closed system, closed meaning no external forces, is conserved, right? Or doesn't change. Because if the change in momentum is 0 for the system, that means our system momentum remains the same, aka it is conserved. So when we did this in class, we talked about how we can get from what we know about Newton's third law to this new idea of conservation of momentum. So here's some other added cool things. So we know that the change in momentum of the system is the individual momentums added together, true. But we also know that the momentum of the system was the total mass times the velocity of the center of mass. And we talked about that in the previous movie. So what this means is the change in momentum of the system is really the mass times the change in velocity of the center of mass. Now, if our change in momentum is 0 in a closed system, then that means our change in velocity of center of mass is 0. So if our center of mass was like 2 meters a second beforehand, then that means our center of mass is 2 meters a second afterwards. And that can have some really cool effects. There we go, that's the word. So not only is the total momentum the same, but the velocity of the center of mass remains the same. All right, so the way you'll usually see this written, this idea of conservation of momentum, right? Because that's not usually how we see it written, because that's kind of boring. How we usually see it written is that the initial momentum of the system has to equal the final momentum of the system, right? And this is the same thing as this because a change in momentum is P final minus P initial. So if I was to subtract P initial from both sides, you get 0 on one side and P final minus P initial on the other. Okay? Now remember, this is for the entire system. So these initial and final momentums are really made up of the individual objects. So the momentum of object A plus the momentum of object B before has to equal the momentum of A plus the momentum of B after. And the way we usually denote the after is with these little prime symbols. And you might recognize them from math, especially with geometry when you're doing transformations. And so we know that these individual momentums are calculated by mass times velocity. So this really starts to look like MAVA plus MBVB MAVA prime plus MBV prime. Lots and lots and lots of subscripts, and those subscripts are important to keep in mind. Okay, so let's do an example with conservation of momentum. So let's say that I have a block of mass M, this is block A, and A is moving to the right at 4V, and then I have a block of mass 2M, which is going to be B, and that is moving to the left at a speed V. Okay. And these two objects can kind of collide in a bunch of different ways, and we can, have a end result in a bunch of different ways. Okay. So they could, bounce off of each other and move in the same direction. Okay. They could stick to each other, or maybe they are bouncing and moving in opposite directions. And we would know that depending upon the problem. It's not like you would have to decide what happens. So let's say, right, so for all of these, this is my initial case. And I'm gonna switch up my final case depending upon how they collide. So let's say they bounce off of each other, but move in the same direction. So mass M is moving with a speed V, right? That's A. And I wanna know how fast is that 2m mass moving. So I would do MA, VA plus MB, BB. And if B wasn't moving, then the initial momentum would be 0. Similarly, if it's not moving after, final momentum would be 0. But I'm doing a kind of trickier case where they're both moving just to show you the math. And then MA, VA prime plus MB, VB prime. Okay, so initially, right, I'm filling in these values. So I have M times 4V plus 2m, and I'm going to substitute it in as a negative v, because remember, momentum's a vector, so direction matters. And then after, I have an m moving at a speed v, and a 2m moving at an unknown speed. I'm not going to use v, so I'm going to say x. That's what I'm looking for. So this becomes 4mv minus 2mv, because adding a negative is the same thing as subtraction, is mv plus 2mx, and x is what I'm looking for. So this is 2mv is mv plus 2mx. I'm going to subtract an mv from both sides. 2mx, and m can cancel, and I could have canceled an m in the second step, but I left it in. And then I got to divide both sides by 2. So this block is moving to the right with a speed v over 2. And now, luckily, or not luckily, eventually, block A will run into block 2 again because it is moving faster. So we'll catch up to it, but it's fine. Okay, so let's say same initial, but now they stick together. How fast are they going? So the important thing to remember is when two blocks are stuck together, they are going to be moving with the same velocity because they're stuck together. Just like in a system that's connected, they have the same acceleration. This is a connected system, so same velocity. So my initial momentum, everything on this side is going to stay the same. So instead of substituting all that in again, I'm just going to go right to the total momentum initially, which was 2mv. All right, so then I have m moving at some unknown speed x plus 2m moving at some unknown speed x. So 2mv is 3mx. Right, and I got 2/3 v is my unknown speed. So when they stick together, the two blocks are going to move at a speed of 2/3 x. So again, just another option. So now let's say the problem tells us that they bounce off of each other and move in opposite directions. So maybe this block moves backwards at v over 2. And we want to know how fast is the 2m block moving. So again, same initial conditions, so same initial momentum. So instead of plugging everything in, I'm just going to go right to the initial total momentum, which was 2mv. And then I got m moving at negative v over 2 plus 2m moving at some unknown speed x. So 2mv is negative mv over 2 plus 2mx. So 2mv plus mv over 2 is 2mx. All right, so I got to add some fractions, and in order to have fractions added together, I got to multiply and get a common denominator. So this ends up being 4 over 2mv plus 1/2 mv is 2mx. So what, 5/2 mv is 2mx. The m cancels, I divide by 2, and I get 5/4 v equals x. So that definitely does have to be moving to the right. Did make my arrow properly. Okay, So what we're seeing here is that that block, that 2m block, ends up moving the fastest when they bounce and move in opposite directions. And that's because when this block M, or when any block changes directions, that's going to lead to a greater change in momentum for that block, which means that this block is going to have a greater change in momentum, which is why we end up with the fastest speed when they bounce off of each other and move in opposite directions. And it looks like we get the least amount of speed when they bounce and move in the same direction. Okay. All right, so let's check our center of mass and make sure that part is true. So remember, we can find our center of mass by doing our total times the speed. So our system momentum was 2mv. Our total mass was 3m. So our speed of our center of mass beforehand is going to be 2/3 v. So let's see, the stick equation, that definitely works, because when the two objects are connected moving at the same velocity, that's also the velocity of the center of mass. So that's a good shortcut, right? Whatever the speed is when they're stuck together, that's the speed of our center of mass. So we see speed of center of mass is conserved there. All right, let's see when they bounce but move in the same direction, right? We can do our other velocity of center of mass equation, which is essentially VA, MA, yada, 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 yada. Okay, so V center of mass for the two objects, and I'm doing this after the collision. So I got MV plus 2mv over 2 plus, and this is over the total mass, so over 3m. So that gives me 2mv over 3m, and I still get that 2/3 v. So center of mass has remained the same as we predicted. We already talked about the stick. So now let's check when they bounce in opposite directions. All right, after the collision, we got m moving at -v over 2 and 2m moving at 5/4 v. Oh boy, this is going to challenge my fractions. So I got -mv over 2. Oh, this 2, okay, it's not as hard as I was thinking. All right, perfect. So this 2 and this 2 simplify to give me 5/2. So 5/2 mv all over 3m. So -mv plus 5/2 mv, that gives me 4/2 mv over 3m. 4/2 is the same thing as 2. And I still get that 2/3 mv. So no matter how they collide, the velocity of the center of mass is remaining the same. And that's because momentum is conserved, because I am in a closed system. All right, and that is it for momentum conservation.